Hey everybody, and welcome back to Calc 3 Online. So the plan for today is just do a few quick problems, some more examples related to double integrals. And to start off, I just want to kind of show you one of these. So we haven't seen one of these yet. So sometimes you're doing a double integral, and you see the inside here is only a function of y. And so we really wouldn't want to do a dy dx integral. It would be much easier, right, if we did dx first, because then you would literally just like think of this as constant, and you would tack an x on the side, and then do like the dy stuff after. So sometimes we want to change the order of integration, but we were given bounds here that are, basically y equals x, y equals 1, and, x runs from 0 to 1. And so we have to kind of think about the picture and figure out how to change the order of integration. So what I'm going to do first is draw what we basically have going on. So we have, in terms of y, right, we have a lower bound of y equals x, so that line, and then we have an upper bound of 1, right, so 1, 1. And then our dx stuff, right, goes 0 to 1, right? So this is just 0 to 1. And so we're basically integrating over that triangular region right there. And right now, like the way I was saying, we're doing vertical first, dy, and then we're going side to side. So if we wanted to take this problem and switch it to a dx dy. Whoops, I didn't do dy. Dx dy. Then we need to look at it as going left and right first, right? So on the on the left side, if we're doing this boundary over here, right, that's 0. And then this one is y equals x. But what your bounds in here, like if you're doing x first, we basically need it to be y, right? Because we need these things to equal, x needs to equal these two things, right? And then, actually the outer bound doesn't change, but kind of our interpretation of it changes. Before we were thinking about x running from 0 to 1, but now we're thinking y is running 0 to 1. So this is still 0, 1, but basically a different variable, right? Y instead of x. And then it's a much easier integral now. So if you go and do this thing out, this whole inside is constant in x, so we can just do x sine squared y, and we'll plug in 0 and y, dy, and then we would get literally just y sine squared y, or sine y squared, and then dy. And this is one where, it's a nice u sub problem, right? Because if you do u equals y squared, then du is 2y dy. And so we have a y dy, so then, du over 2 is y dy. And so since we have a y dy in our integral, u sub makes sense. So we're basically going to switch it to, we can take a half out, and then we're really just going to be doing sine now u du. And if we do that out, we just get cosine, negative, sorry, put a negative on the 1, negative cosine u, but then I'm just going to go plug back in the y squared, and then we're going to do this from 0 to 1. So if we solve all that out, we get 1/2 minus cosine of 1 over 2. There you go. So very common trick. Save yourself, the effort. Like there's a lot of integrals where honestly too, they're like not solvable, at least not nicely, if you do it the way it was given. But sometimes if you do this switching of order of integration, you get something that's really nice. And just make sure that you switch the bounds, because you can't switch. I mean, technically there are some where it literally wouldn't look that different, but those are like the rectangular regions and constants of integration and stuff. But if you have functions in here, they're going to definitely change. You're going to have to change it. You couldn't use x here if you're doing a dx integral first, because then when you go to like do this part, the evaluating part, then you're going to get an x over here, but you're doing a dy integral. So then you're going to get something that doesn't make sense, because you should be getting a number out, not some sort of expression. All right, I just want to do one more example. And so if we just look at what we got here, what this is saying is that this double integral over some region D could be split into these two, okay, these two dx dy integrals, double integrals. And we're asked to basically sketch D first, and then when we sketch it, we'll be able to see that we could actually express this thing as n iterated integral with reversed order of integration. So basically we should be able to do this problem with one integral instead of two double integrals, like one double integral, and it should be a dy dx instead of a dx dy. So I'm going to start by just sketching this thing. So if we, let's just do this here. So I'm just going to tick off a few points here. All right, and if we take, let's just do this one first. So everything I'm going to do in red here is the first double integral. So we know that we're going 0 to 2y in x, right? So left and right. So 0 is just the y-axis, so I don't really need to draw anything there. And then 2y is, just a line that goes through the origin, has a slope of, has a slope of 1/2, right? Because if x equals 2y, then y equals x over 2. So just go up 1 over 2. Let's do one more. Up 1 over 2. So that is the upper bound for the rightmost bound, I guess, for x. And so we're going from the y-axis over to that. And then it's saying that y right here is just 0 to 1. So basically what we get is really we're just going 0 to 1 here, and then we're just moving over to this. So this little triangular region is all I have basically for the first integral, that triangular region. Then we'll do this one purple. So now we got x equals 0 again, and the other bound, x equals 3 minus y. Just add the y over, 3 minus x. If I go ahead and sketch that, so let's see, up here at 3, down 1. All right, we get that line, horribly drawn. And so now we're again going from 0 right here, which is over here, over right to 3 minus y. And then this time we're going 1 to 3 in y. So 1 up to 3 right there. So basically we're getting this triangular region for the second chunk, right? And so if we wanted to do this as a, we're going to do some sort of, forget the function in here, but this time they're asking us to switch it to dy dx, okay? We need to look at it as a lower bound right here, and then going up to this line here, right? And then we're going to go, x is going to be 0 and to 2. So if you think about what this was, that came from this right here. So we need y equals x minus 2 on the lower bound. And then we need this one for the upper bound. So 3 minus x, right? And then we go 0 to 2. So for the x stuff, we're just doing 0 to 2. And that's it. That is taking, this integral, whatever this function is in here. If you did this, or if you did it in 2 parts, you would get the same answer over there. The same integral over that region D.